The last model we're going to look at in this chapter is called the envelope method. And once again, here we are talking about relationships between different inputs. So we had a phase-by-phase input analysis in the first example, and then we did correlation, and then we did coupler, and then we did regression analysis. So now the envelope method. So envelope method is coming up with a equation formula like relationship based on a value of one input, find the value of another input. Okay, so we're going to go back to revisit the Facebook valuation example where we had expert opinion on several variables. So we had revenue growth, cost of goods, R&D, um, and the estimated beta value. They were all um, variable inputs that we simulated. At that time, we assumed that they are all independent. We treated them as independent variables. We assigned different probability distributions for each of them without regard to any interrelationships. But the reality is, often, in reality, the revenue growth is probably very closely related to R&D costs. If you spend more on R&D, then that will result in revenue growth. So if you want a revenue growth to be certain target, to meet the revenue growth target, you have to spend money on R&D. So R&D and revenue growth are kind of interrelated. So how would you model that? Okay, so we're going to look at that interrelated modeling from just one expert. So actually there are three experts if you remember, and we will just take one expert and model it. And this same concept can be applied to the other experts as well. So to keep it simple, we are just taking one expert. And let's take um, expert number 2, for example. Expert number 2 in the original example uh, had three estimates for revenue growth: the minimum, most likely, and maximum. Right? And he, independent of this, the expert number 2 had estimates for R&D cost. So that should be R&D cost 20%, 25%, and 30%. That was the original uh, estimate. Okay. So now we go back to expert 2 and then say, all right, there is a relationship between these two. So why did you look at it and then say, all right, so you've for revenue growth of 15%, what would be the minimum, most likely, maximum for R&D? For 22%, what will it be? And for 35%, what will it be? So now what we can do then is we can take the revenue growth and fit the minimum values to revenue growth, and based on the revenue growth that we simulate, we can fit into that equation and find what the minimum for R&D would be corresponding with that revenue growth. And similarly, we simulate revenue growth and then we estimate the most likely from that equation or from that uh, uh, relationship. And we do the same thing with maximum. So if we fit a regression equation, it may be a straight line, it may be a curved line between minimum estimates of R&D, this is y and that is x. And then this is y and that is x, this is y and that is x. And then we simulate revenue growth and use that simulated revenue growth as x and fit it into this equation to find the minimum, this to find the most likely, this to find the maximum. And with those estimates, then we finish up the simulation analysis. Okay, now let's head on to Excel file. Okay, so these are the estimates that the expert has given us. So that's our input. All right. So now what we need to do is to set up a relationship with this as y, and this as y, and this as y, and then this as x. Okay, so let's we're going to set up a nonlinear equation. So let's see that we do that. All right, so we selected that. So now we need to enter the data. Okay, so we add. Okay, the first one is minimum. The x values are these, and the y values are these. Okay, so that gives us one line. Okay, that. And then we add. Now this one's going to be most likely, and then we have the x values, and then the y values. All right, so that's that. And then one more, the maximum x values and the y values. Okay, so we have three equations and three lines. Okay, let's do some formatting here for this graph. Okay, and we know the x-axis goes from 15.15 to 0.35. Or maybe we can put 0.4 there. So